Okay. Walk, anything we want. Trail. No repeated edge. Path. Can't repeat a vertex. Same idea. A circuit is a trail that's closed of length 3 or more. A cycle is a circuit with only one repeated vertex, the start and end. Now, if you think about the way we wrote paths and trails and walks, we wrote them as lists, yes? And ordered whatever. So something like, where's that picture? U, V, W, X, Y, right? I was going to put circles at all of them, and then I realized there. So I could take a circuit like this, X, Y, W, U, V, W, X. That's a circuit. So let me overlay that directly onto what we've got. X to Y to W to U to V to W to X. By the way, I don't have to start at X. I could pick any one of these and follow that sequence around. But this is our starting and ending point, the way I've written it. That makes these internal vertices. Those are the ones other than our start and end. So when we talked on Wednesday about a UV walk, a walk that went from U to V, U and V were the not internal vertices, whatever else was in the middle there. Those are the internal vertices. The reason I mention this is because the definition in the textbook of a cycle is it is a circuit that does not repeat any internal vertex.
The internal part. Just,
But that's why I know this can't be a cycle, because in this list, I see the same thing twice. In that bracketed piece,
if you were to have another X in there somewhere,
same thing, it'd be screwed.
Okay, so you're allowed to, so even if it's the same vertice at the beginning and end, it.
Right,
can't
it cannot
go
repeat
above.
in the middle.
Okay.
There can't be a repetition of a vertex in the internal section. The fact that in between here, I see something that is somewhere else, even if that thing happens to be one of those. So if I wanted to make a cycle, I could do something like X, W, V, Y, X. Right? And that would go X, W, V, Y, X around this triangle. Well, around that shape. Cycle has a length, right? Because a path has a length, a walk has a length. That has length 4. A K cycle has length K. I didn't want to use the word triangle for this because a triangle should have length 3. And so even though geometrically that looks like its shape is a triangle is a cycle of length 3. And a square is a cycle of length 4. Because remember, we can draw the picture any bloody way we want. It doesn't have to look like that arrangement as long as I preserve the edges that connect the correct vertices. A cycle is even if its length is even, a cycle is odd if its length is odd. Please note, if you have a cycle, then you're not repeating any vertex other than the start and the end. What if you took that cycle and grabbed one of the vertexes and threw it away? Threw away the edges that were incident with that. What would be the thing you were left with?
You took out all the internal?
No. I'm going to take out just one. I'm going to take out any one. It's in a cycle, right? Right? This is the circuit. This is a cycle in particular. Pick one of the letters. Throw it away. What are you left with? If you only use this cycle, X, W, V, Y, X. It looked like that, right? You told me to throw away V, so I'm going to throw away V and I'm going to throw away the edges that were incident with it. I'm left with a path. Every time, because there's no repetition in a cycle, I don't repeat edges, don't repeat vertices, I get a path. If you break a cycle, you get a path. Questions? So if I can find a path from one vertex to another, I say those vertices are connected. I like this idea so much, I'm going to talk about the whole graph that way. If any two vertices are connected, then the whole graph is connected. What does that mean in my picture?
Disconnected vertices.
Well, yes, being connected means it's not disconnected, but what does that mean in the picture? To each other, right? They may not have single edges to each other. They may be a walk, a path, but it means that I can get from any vertex to any other vertex. It's one blob. If G is not connected, then it's multiple blobs. And each blob would be a connected piece, a connected subgraph that is not part of any other connected subgraph is called a component. You will sometimes hear these referred to as connected components. But the word connected in this case is redundant. An example. Here's a graph with 11 vertices. And 10 edges. Right? 1, 2, 3, 4, 5, yes, 10 edges. But it's made of 3 components. The connected subgraph ABCD, the subgraph induced by the set of vertices ABCD, which means we only keep A, B, C, and D and the edges connected to them. That's a component. EFGH, that's a component. IJK, that's a component. Here's a connected subgraph. FG. Right? That piece is a connected subgraph, but it is a proper subgraph of another connected subgraph. That's why it's not a component. The component is the biggest possible connected subgraph for any given collection of pieces. In a sense, really, yeah, it's the parts the graph is made up of. You look at me like I'm a space alien. Talk to me.
Excuse me, it's not a component because it is a smaller section, so would A, B, C, D be a component of this graph?
Yes.
Because it's 4 as well as.
Well, it's the whole thing. It's not a connected part of something bigger. So FG is not a component because it is a proper connected subgraph of a bigger piece of my graph, right? But this is not connected to anything bigger than it.
Okay, so A, B, C, D is a component.
Yes, IJ.
Is component, I, J, K is a component, but any parts of that is not a component, is a smaller part of a bigger connected.
Of a component.
Yes, okay.
Yes, the components are maximal in one sense. You can't make them any bigger without jumping to another piece. They're like islands in a chain, right? I've got the Big Island and Oahu and Kauai. And I can get from one to the other. They're all part of Hawaii, but they're separate parts of Hawaii. This is a graph that has 3 components. So I might talk about the number of components in a graph. Little k of G is the number of components of G. In this example, we have 3 components. Hey, wait a minute. If a graph is connected, how many components does it have? One. They'll all be on the same blob, won't they? Don't kill me. Let's say that 2 vertices are related if they're connected to each other. Discrete math, chapter 9, relations. I know you did it last spring. I'm going to do it again. I'm actually going to say U is related to V if U and V are connected. Remember when we were doing relations, we looked at properties. We asked whether or not relations were reflexive and symmetric and transitive. This relation is reflexive and symmetric and transitive. Can I get from U to U? I don't have to go anywhere. If I can get from U to V, can I get from V to U? Same walk, just go backward. If I get from U to V and V to W, can I get from U to W? I don't have to have a path, I just have to have a walk. Yes. That makes this an equivalence relation. And the collection of vertices then get divided into equivalence classes. Now, you're looking at me going, right, whatever the fuck you say, man. modular arithmetic. When we did the remainders, when you divide by 0, when you divide by 3 are 0 or 1 or 2. We had all the numbers that could be divided evenly by 3. And all the numbers that were 1 bigger and all the numbers that were 2 bigger. But then we realized if we added, you could pick any number in one set and any number in the other set, you get the same set as the answer. Those were the classes, the components of my graph are the classes for this relation. So really, when I think of what's a component, I think about what things are connected to each other. So that's why I didn't just say F and G were a component, because they were also connected to E and H. And I can get from F to E, and I can get from F to H. So I need to include them in the class. I need to include them in the component. That's what I mean by they're as big as they can be without jump. Still iffy.
Yeah, added more words, I got them before and now I'm like.
No, all I'm saying is you did this back then. It's the same idea. By definition, every equivalence relation creates these classes. In discrete, I talked about students by the number of credits they take, right? If you've taken 0 to 29 credits here at Seton Hill, you are a freshman. If you've taken 30 to 59, you're a sophomore. If you've taken 60 to 89, you're a junior. If you've taken 90 or more, you're a senior. You tell me how many credits you have, I tell you the group. Period. And you can't be in more than one group. And you can't be in two groups at the same time. And two groups have to be completely separate from one another. My components have that exact same behavior. Pick a vertex. Everything that I can reach from K is the connected component containing K. So I start at K and I say, where can I get? That's my component. So I have 3 components because I have 3 different things I can start at and build out that far. No further. So that means that every vertex belongs to exactly one component. If G is disconnected, and U is in component 1 and V is in component 2, then there's no possible edge or no walk from U to V. That's what being in different components means. Now, again, here's an interesting idea. Let's suppose I have a graph that's got at least 3 vertices. Got at least 3. I'm going to pick 2 different ones, U and V. If I take away U and I look at the rest of the graph, and that's connected, And I put U back and I take away V and I look at the rest of the graph. That's connected. Then the whole graph has to be connected. What the? Why is that true?
If U and V are connected, then whenever you remove the U or V, you have to get rid of the edges, so if anything else was disconnected. They couldn't possibly be a part of the same thing.
I'm not sure I buy that complete argument, but I think you're onto something. Hold that thought.
What if it's like a straight line, so you said three different components or?
I know, if it's one line, right? Pick one vertex. Take it away. It isn't going to work for any pair of vertices, right? It's going to work for some U and some V. I've got a straight line. Let's take the one on each end. If I take away U, isn't the result still connected? If I take away the other end, isn't the result still connected? Then when I put them both back, the whole thing must be connected. But then that wasn't one of the U or V I should pick. This isn't for an arbitrary set of vertices. It's for two particular vertices. And I don't know which ones they might be. But that's the question. How do I know which two vertices to pick? If it contains two vertices so that this happened. If there were 100 vertices, maybe 97 of them that I took away would break the graph. But maybe there are a couple where if I take away this one, the result is connected. If I take away this one, the result is connected. Knowing which vertices are going to break the graph and which ones aren't is something that's important, and we'll get to that. There's a name for those things. But I want to think about this. If I want to show that G is connected, let's do this direct proof. Proof. Suppose G is a graph of order 3 and there exists U comma V in the vertex set of G, U not equal to V, with G minus U and G minus V connected. I want to show that G is connected, right? I want to show that G is connected. So let's pick any two vertices. Let X and Y be two vertices in the graph. Any two vertices at all. There are two options here. Either I pick both of my special vertices U and V, or I don't. Let's start with the assumption that I don't. Maybe I pick one of them, but I don't pick both of them. So let's suppose I didn't pick U. I may have picked V, but I certainly didn't pick U. By the way, if you don't like me using U, use V. Without loss of generality, I assume I didn't pick U. But that means X and Y are in the graph when I take away U, right? Because I didn't pick U as one of these. So if I take away U, I still have both X and Y, right? What do I know about this graph, G minus U? It's connected, which means that it's from X to Y, isn't it? Sorry, a walk from X to Y. And if there's a walk, there's a path. Perfect. I can get from X to Y. If it's there when it's in G minus U, what happens if I put U back? I don't care. That path still exists, right? P is also an XY path in G. I can get from X to Y. Yay! All right. So if I didn't pick both of these to be my special vertices, it works. What if I did and picked both of them? Case 2. Crap, I picked them both. So really, I don't need the letters X and Y. I really just need the letters U and V. All right, well, let's just name them in this order. Without loss of generality, assume U is X and V is Y. Hey, wait a minute. The graph is of order 3, right? The graph is of order at least 3. That means there's another vertex somewhere around here. Let's give it a name. W. The order of G is 3. Is at least 3. So there exists W in the vertex of G, W not equal to U, W not equal to V. Hey, wait a minute. In G minus U, there's a path from W to V. Why do I know that? I'm trying to show there's a path from U to V. I don't know there is one yet. But I know there's a path from W to V in G minus U because G minus U is connected. So if I take away U, I can still get from W to V. Let's call this path P1. Let's do it the other way. Take away V. In G minus V, there's a path, I'll call it P2, from W to U. Again, because G minus V is connected. So I've got this third place I can go. If I don't worry about this one, I can get from that one over there. Don't worry about this one, I can get that one over there. Let's glue these two paths together. What happens when you glue paths together?
You could make a bigger path, but it's not guaranteed you're making a bigger walk.
The other way around. I will make a bigger wall. I don't know that it will be a path.
I just saw that. You don't know if there'll be a bigger path, but you'll be making a bigger walk.
I'm sure do that.
Okay. I was just like,
No, I missed her. I thought you said I can't make I can't make a bigger path. I can make a bigger path, but I won't know if it's a wall. I missed
I
her.
started with that initiative to walk.
Okay. No, I will create a walk, but if I have a walk, then I have a path, right? Because if I have a walk, I can eliminate all the loops and all the extra bits, and I will eventually get a path. If I take P1 union P2, I get a walk. It goes from V to U, but it goes through W. So I first say, I'm going to go over to W, and then I'm going to go from there to U. I'll have to take P1 backwards, right? Because P1 is written going from W to V. So I want to go from V to W. Let's say backwards on P1.
In the professional math room, do you always have to write things in words, or can you use graphs and stuff to define it versus talk like this, because it's ridiculous.
So the problem is that the pictures aren't always.
I feel like it's this.
Well, it's very general. I mean, you show it for this one example. I'm gonna show it for all possible graphs. That's why I'm making words. See my problem? But if I have a walk from V to U, then there exists a path from V to U. Therefore, in G is connected. Because I can get from any vertex to any vertex. This time I happen to pick the two special vertices. I can get from one to the other. Damn, it worked. But you're right, Roman. I have to make sure I pick the proper two vertices to be my special ones. Some graphs, all the vertices are special. Some graphs, only a couple of them. I specifically said we needed a graph of order 3. Why?
It was less than 5 and take away 1. So it'd just be like 1.
Let's think about that. A graph of order 2 only has 2 dots, right? Here's a graph of order 2 with no edges. If I take away U, that's connected. If I take away V, that's connected. That's not connected. Motherfucker. So really, I do need that third one. Otherwise, this is a counterexample to my theorem. But as soon as I have a third one, it does work, no matter how many edges I have. By the way, if you only had 3 vertices, you really only have a couple of options for a graph. You could have a triangle, right? You could have 2 of them connected and 1 not. If you took away 1, you'd have a connected piece. But then if you take away either of the others, you won't have a connected piece, won't you? So it's not connected. And if you have no edges, well, then you're in this case, aren't you? You're not connected. So you could actually go through all possible graphs with 3 vertices to show why it works only in the connected case. 4, 5, 6, too many vertices, too many edge possibilities. If I have 4 vertices, I have 6 possible edges. And I can take away a bunch of them and still be connected. So there are lots more options when I get bigger numbers.
You had 6 vertices, but they were 2 component triangles.
Okay.
And you take away.
It's not connected, right?
Okay, so the entire graph has to be connected.
That's what you're trying to show. Look at the theorem we started with here.
I know that you mean that you can do it with 2 disconnected triangles if you take away 1 vertex to prove that they're not connected.
Sure. In order for me to do this, I have to pick 2 vertices. So that when I remove those 2 vertices, no matter which 2 I remove, the result is connected. Remove 2 vertices from 1 triangle, it's not connected to the other piece. Remove 1 vertex from each triangle, still 2 components.
Okay, so it's saying that everything has to be connected, not just connected to a few things.
The whole graph is connected. Not each component, the whole Megillah. If it's connected when I remove the 2 bits, then the whole thing will be connected.
And that's great, we got the answer, I was talking about the actual theorem, it never says that like. It just says if you remove this part, then the rest is.
If I remove one vertex, the thing has to be connected. If I remove the other vertex, the thing has to be connected. So when I remove one vertex, is this connected?
No, but it doesn't mention all of the vertices have to be connected, it just says it has to be connected.
Well, that means that every vertex is. That's the definition of being connected as a graph. Let me back up.
B minus B.
Right.
Is connected.
Yeah.
It's not talking about, it's talking about the entire graph?
It is talking about this graph.
G minus B, okay, so
So-
everything has to be.
All of those bits must be connected when I take away V. Yes. When I say thing is connected, it means all of the vertices in that thing are connected to one another. Okay. I like connected graphs. They represent real maps and things like that. That's helpful. If I have a connected graph, and I pick two vertices in that graph, there might be more than one path between U and V, right? I know since G is connected, there exists at least one UV path. But there could be more. How do we define the length of a path? Okay. The smallest possible path from U to V is called a geodesic. And the distance from U to V is the length of that geodesic. It is again still possible to have more than one geodesic. But if the distance from U to V is some number K, then I have a path that looks like this. It starts at U, that's vertex 0. Next. It ends at V, which is vertex K. That means there are K edges exactly. Well, it turns out there's a really nice thing. If this is a geodesic, then the distance from U to VI is exactly I. Because this is the shortest way to get from U to V, it's got to be the shortest way to get to any of the other stops along that path. If there was a shortcut, you'd take it and get a smaller geodesic, wouldn't you? And geodesics are as small as you can get. They're the fastest possible ways to get there. If two vertices are neighbors, if they're adjacent, then their distance is 1. Every time. If G has some number of vertices, say n, then the biggest possible geodesic is n minus 1, provided that graph is connected in a straight line. You just go from one end to the other. That's the biggest possible geodesic. That's exactly n. Sorry, n minus 1, because there were n vertices. If I give you any graph, we can rewrite that graph by distance. Here, page 16. Here's a picture. They've already picked a vertex. It's in black. T. What are the vertices that are distance 1 from T? And those are the only two that are distance 1, right? Because they're the only that are adjacent. What's distance 2 from T? But wait, there's more. Q, R, V, and Y are all distance 2 away. But what about Z and S and W? They're all distance 3, aren't they? Imagine you made this out of beads and string, and all the pieces of string were exactly the same length. Tinker Toys, would that be better? I don't care. You grab T and you pull up, and everything hangs. They'd hang in layers by distance. U and X are distance 1. Q, R, V, and Y are distance 2. S, W, and Z are distance 3. We've remapped this graph, just changing the picture to show the distances. What is the biggest possible distance between any two vertices on this graph? That might take a little work. What if I started at this vertex? Would it take me 3 steps to get anywhere else? Ooh, are we sure about that? I want to go from Y to S. Can I do it in 3 steps? Y to U to R to S. Yes, I can. If I want to go from Y to Q, can I do it in 3 or fewer steps? Yeah, to U and to Q. So yes, it may be 3. The greatest possible smallest distance is called the diameter of a graph. It turns out that this idea of being a diameter means that if I know the shortest path between two vertices is exactly that long and I pick another vertex, then going that way would be longer. We did this in Calc 3. We did this in trig. We called it the triangle inequality. the shortest path goes from here to here, and you pick somewhere that's not on that path, you've got to be going a longer distance. By the way, that if you remove this one and remove this one and those two pieces are still connected, then the whole thing is connected, that actually turns out to be an if and only ifs. The proof of the converse is in the text. I really, really like diameter. Measuring on graphs becomes important. More general ideas and specific types of graphs on Monday. I will see you all then. Have a wonderful evening. You don't have anything due to me on Monday.